Hey guys, welcome back to Chris V's RF Designs. So in this video I'm finally moving away from designing low noise amplifiers to the next part, which is a mixer in a radio frequency integrated circuit design. So I want to be brief about something else. My website with my software has been deleted because my web host will be charging me over $200 a year to sustain the website, and my website is not making any kind of money, so there's no way for me to keep that website there on my web host anymore. So I will hopefully find another route for this so that I can create another website with my software on it, and you guys will have to stay tuned for my next website. So what is a mixer? A mixer can either up convert or down convert frequency. And why would you want to do that? Because receiving a signal with a modulated signal at 2 gigahertz would be very difficult to obtain the message signal at that frequency. To create a circuit like that would be very difficult, and also so what you would want to do is down convert that frequency to, for example, 100 megahertz, and having that as the modulated signal and retracting the message signal from that modulated signal will be a lot easier. So that is the number one reason for creating a mixer in your circuit design. Another reason could be that if you keep on amplifying further amplifications at 2 gigahertz, it would be prone to oscillations, be very prone to oscillations, versus if we down convert it to 100 megahertz. So there are two types of mixers. There are active mixers and passive mixers. Active mixers use transistors to amplify the signal even further, but they are prone to distortion noises, and on the other hand, the passive mixer is prone to losses, but it would not have distortion noises. So there are reasons why you would rather use a passive mixer versus an active mixer. So in a passive mixer could contain, for example, 4 diodes and as a bridge rectifier, and if we wanted to solve for the input impedance of those 4 diodes, we need to take baby steps to find the impedance, because this is the first time I've ever used harmonic balance to solve for the input impedance. So let's go with 1 diode first, and then in the next video I will put together all 4 diodes and solve for the input impedance of that. So anyway, I forgot to tell you, I'm going to go ahead and try to implement my software so that we could calculate these input impedances of nonlinear devices like diodes here. So let's go ahead and go on to finding the input impedance. of one diode here. Here, for example, could be my low noise amplifier with a 0.1 volt peak and has a sine wave at 2 gigahertz. As soon as that hits the diode, it creates different frequencies, different voltages at multiples of 2 gigahertz, and also intermodulation tones and so on. It can create different voltages that need to be added together in order to obtain a full total voltage input, and also for the current, and everything in the diode is nonlinear. Has everything in the diode. The junction voltage here has harmonics also. So we have to find those values, and to find the input impedance, we would do Vn fundamental divided by the current input fundamental. But we don't know. We could go ahead and solve for that using the Kirchhoff's current law and everything. But it's very important to understand how to use Newton's iteration process to find the values to become more precise. We want to be as precise as possible with the input impedance so that we can create a clean signal that can go through our circuit here. So harmonic balance is basically we're finding the harmonics of the voltages and the currents and in order to find the voltages and currents, we can plug those values in, but they're not. But the linear equation, this is a linear equation here, and this could be example of our nonlinear part. And if they don't equal, then we have to redo a process called Newton's iteration to find new values of our harmonics in the equation here. So that's that. So if we do Vn minus the junction voltage divided by the resistor, the series parasitic resistor here, we get In. So In would be that. And the current is going through your junction capacitor. This would be the current in your capacitor, and then plus the current going into your nonlinear element, which is the Shockley diode equation. So let's keep on going down. Here I'm going to skip this part, but you can read it if you want. We could form the Jacobian now, but we haven't computed the values yet for Vj, Vj prime, Cj, or Cj prime. So I'm going to skip this. So I'm going to skip this part for now, and here are the parameters you would get in the data sheet for the diode, and I'm using Nyquist sampling with exact precision. Nyquist is just 2 times the harmonics, so N is the number of harmonics you're using, and I'm using 5 tone, which is 5 harmonics, and so it's 5 times 2 is 10, plus 11 is, plus 1 is 11, and then times 2 is 22. So there will be 22 samples that we need to take in the sine wave. To obtain all the time samples. So at 2 gigahertz sine wave, 22 samples of them will become these in seconds. They'll give you these time samples here. At first I thought I was supposed to put those values into the voltage source equation, but I was wrong. We have to start with the frequency domain guess first, and I will show you what I mean by the guess. So in Newton's iteration process, we set all the harmonics that are multiples of that frequency. We set them to 0 to find, because we don't know what they are, but we do know what the fundamental is at 2 gigahertz. But we do not know the Fourier transforms of those values yet. But we do know it for the fundamental, and the fundamentals are k is equal to -1 and k is equal to 1. So there's negative and positive because you need to add the negative frequencies with the positive frequencies to create a full the actual input voltage in the time domain at that sample. So we will do an example here. Let's figure out how do we get this part here. So at the fundamental, if we find the in the frequency domain voltage, we find the frequency domain voltage by taking the Fourier series, the Fourier transform of the voltage supply, which is 0.1 sine omega t, where the fundamental is 2 gigahertz, and when we do the Fourier transform of that, we get J 0.05 and also negative J 0.05. We do not, it's not part of this equation because that is part of the equation to solve for the time domain input voltage. So we'll do one together here. So at n is equal to 1, n is equal to 1, which is the second sample. So instead of having to represent, instead of having to put in the time number, because those are so huge, we don't want to do that all the time, so it'd be easier. We can express omega naught Tn as equal to 2 pi n over m. The small n is the sample, and m is the number of samples, which is 22. So if n is equal to 1, we would have 2 pi times 1, negative 1, or 1, sorry. 2 pi times 1 divided by 22, which is just this. And then you have your k value here. So if we plug in negative 1, so 2 pi over 22 reduces to pi over 11. So if we multiply that by negative 1, we get e to the negative j pi over 11. And you do this for k is equal to 1 also. But we do not know what the other harmonics are. But in order to find the other harmonics, we use Newton's iteration process to find them. So as you can see in the equation, what we found for the fundamentals, it has an exponential form here, and we can convert that to an imaginary number using Euler's formula. So what we have up there is k is equal to negative 1, we have negative pi over 11. So negative pi over 11 would go into the theta here and here also, which is right here. And we're multiplying that by our frequency domain voltage, input voltage, which is J 0.05. And then we're adding it to the negative part here. We're adding this also. So at n is equal to 1, we get 0.02817. If you add all the expressions with its corresponding k value, you get all these values. So we do 1 for each n, from 0 to 21. Yeah, and it's a lot of math, so tedious math. So I used ChatGPT to give me all these values here because it's so tedious. And I thought I needed to take the derivative of the input voltage, but you do not. I didn't have to do that because it's not part of the equation that we created for the Kirchhoff's current law here. There is nothing that has to do with Vn in here. We have junction voltage instead. So that's the next part we need to solve for, is the junction voltage. So the junction voltage is just the voltage division of the impedance of the capacitor divided by the resistor plus the impedance of the capacitor times our voltage input harmonics. So we do not include the nonlinear element here. I thought we would need to also, but I read that it has a large resistor value in it, and so it's not going to make much of a difference of what the junction voltage is going to be, because our capacitor input impedance of the capacitor is much smaller. So we could just go ahead and negate that. So we can say that the junction voltage is just the impedance of the capacitor divided by the resistor plus the impedance of the capacitor. Multiply that by our input voltage harmonics. And you can see down here, that's what I did. So we don't need to do Vn prime, as I said. So here are the fundamentals, the junction voltages at the fundamentals, as we only found the fundamentals right now. All the other harmonics we have not found. That is taking place during the Newton's iteration process. But so we found we know what ZAC is because we have the junction capacitance, and we can find the impedance of the capacitor here, which is negative J 442.1. So if we plug that into our voltage division equation, like here, it would be 442.1 divided by 442.1 plus 25. Alright, and multiply that by J 0.05, which is our frequency domain voltage. Harmonic, our fundamental harmonic that we found. And you plug them in, plug these values in for the Fourier transforms of them, and then we're multiplying it by E to the exponential polar form, which I showed you before. We can change that back into complex numbers here and plug in the argument, which was, for example, negative pi over 11 here, and then plug them in, and we get a result for n is equal to 1 as right here. So we could do n is equal to 2, for example. All we would do is we would plug in, let's see here, n is equal to 2. So you would do 2 pi times 2 divided by 22. That would be 4 pi over 22. So it'd be 4 pi over 22, and then we would be multiplying that by our harmonic k values. So we're doing negative 5. We don't know what our V negative 5 is, so it's 0, and so it's 0 here. But if we plug that in for 4 pi over 22 here, with k is equal to negative 1, we'll get this. But with 4 pi over 11, 4 pi over 22 instead of pi over 11. And you would keep on doing that continuously from 0 all the way down to 21, which is 22 samples. And now we need to get the derivative of the junction voltage, because that is part of our Kirchhoff's current law. With the capacitor, we need to find the derivative of the capacitor voltage. So we get this equation right here. All it is it was before it was just VJK e to the JK omega naught t, and if you take the derivative with respect to time, we just take the JK omega naught and bring it out here, and that is the derivative. And so we plug in our values for Tn to 0 and for n, and then plug in our k values here, and we get all this. If we add all the expressions at each time sample with its corresponding k value, you get all these values here for the junction voltage and the derivative. Alright, and now you need to also compute the junction capacitance. There's a standard formula used for finding the junction capacitance in the diode. Since it's nonlinear, it needs to be used for that. So FC we found is in the data sheet is 0.5. The junction voltage in the data sheet was 0.7, and if we multiply those two together, we get 0.35. And we need to see if it's going to be greater than or equal to VJN, which is our time domain junction voltages. We have those values right up here. Time domain junction voltage right here. So these are all the time domain. As you can see, that all the values are less than 0.35. So we would be using that first equation right here. Now on the other hand, if it was greater, then we would be using this equation. So I plug in the real values, the voltages of Vn in the equation, and all the parameters that were given in the data sheet, and we do that for n is equal to 0 all the way to n is equal to 22, or 21 I mean, which is 22 samples. And then we take the derivative of the junction capacitance, and because so this part is not in the it's not part of the Kirchhoff's current law equation that we created, so it's not part of that, but it is part of the Jacobian, as I showed you up here. We would be computing right here the derivative of the junction capacitance. So you take the derivative of that and do the same process with your voltage values and all the values that you have in your data sheet, and you keep on adding these together and you get all these values for our the derivative of the capacitance. So down here is finally we are going to find if our equations equate to 0. So residuals, this is RK, which means residuals. Residuals are numbers that are very small and almost equal to 0. So if we can get those residuals to almost to 10 to the negative 10 power, then we're doing good. But if we're below that, then we need to redo it again. We need to do Newton's iteration process and to find new values for our junction voltage. So linear part minus the nonlinear part. So they are going to have different values, and that will create a small number. And we need to make sure that they're equal to each other. So that is the reason for the harmonic balance of this. So we have the values for VN1, for the for the fundamental voltage at the input and also the fundamental junction voltage. We have those values we calculated up there, which became here, and then divide that by 25, and we get a fundamental input current of this right here. So you could go ahead and actually use this value to plug into your input impedance with the input voltage at the fundamental also, which is J0.05. And if you divide those, J0.05 divided by this, you would get your impedance. But if your residual is not close to 0, then it's not going to be accurate. That impedance that you calculate is not going to be accurate. So at least we have the values here for the fundamentals. And then when you add all these together, when you add all of them together with their end values from 0 to 21, we get these values here. So these are our the guessed values. I think I told you what the guessed values were before. They're just the fundamental components, frequencies that we know, but we don't know these values, so we keep them 0. So that's our guessed values. And now we want to go to the nonlinear equation. And so we have the values for our junction voltage in the time domain. So this is our Kirchhoff's current law we created up at the top, up here. We created that equation. And we have Vj of Tn values, and we have our derivative of the junction voltage in the time domain, and we also have the equation for our capacitor where we can plug in our junction voltage in the time domain in that also. So we have everything that we could compute. So going from n is equal to 0 all the way to 21. These are all the current values for In using the nonlinear part of the equation. So this is not nonlinear. We could have actually put that on the other side of the equation and said that the linear part of the whole thing is equal to the nonlinear part. But it all equates the same way, so there's no need to do that. So when you take the discrete Fourier transform of our values here, so equation to get I and K values, which are in the frequency domain. So 1 over m is 22, so we're going from 0 to 21. And In of Tn, we have all the values right here for In of Tn. And we can plug those in and start from k is equal to -5 all the way to 5 to get these values. And then when we will do an example, for example at r -5, residual -5, we get our input current that we guessed at the junction voltage at -5, which is 0, because we don't know what that value is. So, and then subtract by our In, and using the nonlinear equation, and we get this value at -5. As you can see up here, it's right here. Subtract the two and we get our result here, which is the same as this one right here. And keep doing that from -5 to 5. As you can see that the residuals are to the -6 power, so we could redo this again using Newton's iteration to find new values. So now do 1 Newton iteration to get smaller residuals. You don't have to do the Newton iteration if your residual is very small, meaning good approximation, and you don't have to form the Jacobian. The Jacobian is part of the Newton iteration process. So we will be doing 1 Newton iteration. So to calculate the time domain Jacobian first, that will be 11 by 22 matrices. That way you can easily calculate the the frequency domain Jacobian. Okay. So the Jacobian is just the partial derivative of your input current with respect to Vm. Vm is actually the harmonics. So when we change the harmonics a little bit, we will figure out what our input current would be. So how did I get this equation here? So from this one, so In of Tn, let's don't go up there. Alright. So I used some of ChatGPT to help me with learning the process of harmonic balance and everything. But it's nicer if you could listen to somebody else how they did it, and you could do this a lot easier and faster than it took me to learn. So ID, so this is the current. So this is the Kirchhoff's current law for a parallel model. So I used the parallel model first, and I found out it was wrong. But it literally took me a month to do all this because of how all the math I had to do and understanding everything and everything just to get the input impedance. But that's for this equation here. As you can see, that's the same as this equation here. So if we'd use the series spice model with the series resistor there, we don't include that resistor in there in the we don't include it. So it would literally just be this plus the capacitance, nonlinear capacitance. Alright. And here it kind of shows you how to do the derivative, the partial derivative here of the Jacobian here. So you get this whole value here with this e to the jm omega not tn. So later on I'll try to understand the derivation of the Jacobian, but for now I'm going to let ChatGPT figure out for me right now. So in our case we eliminated the RS for the series model, and you're just left with this equation here. Okay? And now we can plug in the values. We can plug in our negative K, our voltage at V negative 5. And Tn, our N values. And we do the current versus the voltage. So there's a matrix that shows you, so for n is equal to 0, you get all these values here, and all the way to 21. That's the time domain Jacobian. So what we want is the frequency domain Jacobian. So what we will do is just do the summation from 0 to 21, multiply that by 1 over 22, and then just plug in our values as we have up here into the time domain Jacobian, and we can find all the frequency domain Jacobians here from -5 to 5. Alright, so Fk, which is just the residual, this could be R instead, which is just the residual, which is Ik minus Vk. So Kronecker delta is if k is equal to m, and in our case our k is equal to m is 1. So we just add the impedance, the characteristic impedance, which is 1 over, so in order to find the characteristic admittance, it would be 1 over the characteristic impedance, which is 1 over 50, which is 0.02 Siemens, and we add that to our Jacobian here, and we get all these values. Now solve for voltage update. So we found the Jacobian, and all we have to do is do the inverse of the Jacobian multiplied by a -1 and then multiplied by the residual vector. So we have our residuals and we have our Jacobian. So now we can multiply those two together to get our next vector of our delta V, which is how much more we need to change our harmonics by. And then you would do delta JVM, which is all the values that I computed right here from the Jacobian and the residuals. And you get the new values right here. And the new values, you would do the old plus delta JM, which is how much more we need to change the voltage, the harmonics, to see if we can get a better result here. Okay, so now we do second iteration, and so we can plug in our new values that we got up here and plug them in here, and we can add all these. Hold on. Okay, these are the values we get from here. So you could plug in these values up here into this equation from -5 to 5, and we'll get our new junction voltage in the time domain down here from n is equal to 0 all the way to 21. And now plug back into IN, Vj of n, and then recompute DFT to get your current in the frequency domain, which are all these equations. All these right here. And then find fundamental impedance. So basically, we have the current here at so we look at the fundamentals, and we plug those into our impedance. So Vn is now equal to Rs times our In of Tn plus our junction voltage. And so we get these values for our new input voltage. And so you can now do your new input voltages, and actually it came out to be -J5 again, but it changed the current, which now if you do this divided by that, you get the input impedance, which is 25.6 minus J 440.4 ohms. And you could do the output impedance too, because we know what VJ1 is, and we know what IN1 is, which would give you the output impedance right here. And that's it, guys. I hope you liked my video, and please subscribe, and you guys have a good one.